Hello everyone, my name is Greg, and today I would like to walk you through 6 questions from latest performance exams seen in the last 30 days. Topic for today is Performance Class Alpha Theory. Question number 1. Which of the following statements is correct regarding effect of displacement drag and impingement drag on takeoff performance? There is a positive or negative effect in case of a rejected takeoff, and a positive or negative effect for continued takeoff. Let's talk first what these two types of drag actually are. Displacement and impingement drag are both connected with a contaminated runway. Displacement drag results from the tires requiring extra energy to move through contaminants. Impingement drag, on the other hand, is caused by the contaminant particles being thrown on the gear, fuselage, and wings. Both of them are increasing the takeoff roll and are making acceleration harder. Therefore, they would have a negative impact in case of go decision during takeoff. In case of rejected takeoff, on the other hand, there's all kinds of drag. They will have a positive impact on braking action. So the correct answer is answer number 4. There is a positive effect in case of a rejected takeoff and a negative effect for continued takeoff. Now, this question is a bit tricky because you might ask yourself, how come a contaminated runway will have a positive influence on braking in case of RTO? And obviously, it won't. We have to make sure that we fully understand what examiner is asking us here, because this question is not about the influence of contamination as a whole in case of RTO. It asks only about the influence of displacement and impingement drag, so about the portion of factors that influence aircraft performance on contaminated runway. So, like I mentioned before, answer number 4 is correct. Question number 2. Which of the following statements is correct for a turbojet airplane climbing the constant Mach number above the Tropopause, assuming standard conditions? And we have to find out what will happen with indicated airspeed and true airspeed. Let's start with a small review what a Mach number actually is. Mach number is a ratio between true airspeed and local speed of sound. Local speed of sound is only dependent on the temperature. That's very important to remember. In this question, the aircraft is climbing above Tropopause, where, assuming EASA conditions, the temperature is constant, therefore local speed of sound will also be constant. If we put all that in our Mach number definition, knowing that we are climbing at a constant Mach number and constant local speed of sound, we can see that true airspeed also has to be constant. Now, during climb, the air density is decreasing. Since the aircraft is in question is climbing at constant true airspeed, the reduction in density will lead to decrease in dynamic pressure and subsequently decrease in calibrated airspeed. And so answer number 2, indicated airspeed decreases and true airspeed remains constant, will be correct. There is a very nice mnemonic, chicken tikka masala, where you can easily remember the relation between calibrated airspeed, true airspeed, and Mach number. And answer number 2 is correct. Question number 3. The lift coefficient decreases during a glide with a constant Mach number, mainly because a glide angle increases, thrust decreases, and aircraft mass decreases, indicated airspeed increases. For this question, once again, we have to consider the relation between calibrated airspeed, true airspeed, and Mach number. So just to review, Mach number is a ratio between true airspeed and local speed of sound, where local speed of sound is only dependent on the temperature. Now, since we are during glide, assuming the EASA conditions, the temperature will increase, hence the local speed of sound will increase as well. In these conditions, to maintain the constant Mach number, the true airspeed has to increase as well. Also, during the descent, the increase in density causes the increase in dynamic pressure, therefore indicated airspeed, or to be more precise, calibrated airspeed increases as well. Now, let's talk a bit about the lift formula. Lift equals to dynamic pressure, so indicated airspeed, times surface of the wing, times lift coefficient. Since we are in a glide, we assume an accelerated flight where lift is constant. We already found out that the indicated airspeed will increase during the descent. Therefore, only part of the formula that we can change without changing the configuration will be the lift coefficient, which we have to decrease. Now, the lift coefficient is influenced by an angle of attack, the thickness, and camber of the airfoil. In other words, since we do not change the configuration, descending with a constant Mach number, we have to constantly reducing our angle of attack. So coming back to the question, the lift coefficient decreases during a glide with a constant Mach number, mainly because the indicated airspeed increase. Question number 4. And it is a correct one. Question number 4. For performance class alpha airplanes, the Tyre-Speed limited takeoff mass is determined by the lift off speed or rotation speed, which is expressed as a true airspeed or ground speed. So every tire has a rating for the maximum ground speed that they can be safely used for a combination of prevailing conditions and aircraft mass. In Airplane Performance Manual, CAP 698, in section 4, which contains data for medium-range jet transport, you can find figure 4.6, which presents a graph for tires certified for 225 miles per hour ground speed with flaps 5 set. From this graph, we can find the tire speed limited mass, which is plotted against outside air temperature and pressure altitude. Below this graph, we have also certain corrections that needs to be applied if necessary. Now, for this certified ground speed, this graph compensates for the ADST as well as it provides corrections for headwind or tailwind. Hence, the speed used for a determination of the tire speed limited mass is actually V liftoff, expressed as calibrated airspeeds. If you think about it, it makes perfect sense since the lift-off speed is a speed at which the tires from the main landing gear leave the ground, and the rotation speed, on the other hand, is only a point where a pilot starts to apply pressure on a stick, and the wheels are so on the ground at that moment. So, the correct answer for this question is answer number 4. The tire speed limited takeoff mass is determined by the lift-off speed, which is expressed as a ground speed. If you're not familiar with CAP 698, I would highly recommend you to download it from UK CA website. It's a very helpful tool. Many questions are based upon it, and moreover, in some CAs, you can actually use it during exam. Okay, so answer number 4 is correct. Let's move on to question number 5. The performance limited takeoff mass is defined as, and we have 4 different options like always. So performance limited takeoff mass is the heaviest mass at which an aircraft can depart, satisfying a variety of performance limitations. This mass is the lowest from field length limited takeoff mass, climb limited takeoff mass, obstacle limited takeoff mass, and tire speed limited mass. Field length limited takeoff mass, also known as runway limited takeoff mass, is a maximum mass for takeoff, taking into consideration factors like the runway length, runway surface conditions, runway slope, as well as configuration of the aircraft, pressure, altitude, or, for example, temperature. Climb limited takeoff mass is a maximum mass at which aircraft can satisfy the net takeoff flight path climb gradients. Please remember that these gradient requirements are for still air conditions. Therefore, wind does not have any effect on climb limited takeoff mass, unlike on obstacle limited takeoff mass, where the minimum gradient is established with respect to the ground. The tire speed limited mass is established because every tire has a maximum certified ground speed. However, it is a very rare situation that tires with limited mass would be a restrictive factor for performance-limited takeoff mass. Since it requires very unfavorable conditions that would set very high ground speed in relation to calibrated airspeed V liftoff, such as hot day with a high pressure altitude with a stroke tailwind. So, as you see, all these factors limiting performance-limited takeoff mass are connected to the aerodrome itself, runway design, vicinity of the aerodrome, or conditions prevailing on that particular day. Therefore, answer number 1 is correct. The performance-limited takeoff mass is defined as the takeoff mass subject to departure aerodrome limitations. I know that at the first glance, the answer number 4, maximum permissible total airplane mass at the start of the takeoff run, might seem correct as well, but it is a definition of maximum certified takeoff mass, sometimes called also maximum structural takeoff mass. So, answer number 1 is correct. Question number 6. Consider a scenario where you are calculating takeoff speeds for a contaminated runway and you choose a wet VWAP. Do you expect this to be higher or lower compared to the V1 for dry runway conditions? V1 is a decision speed, and it means that if a failure takes place at the most critical moment, close to V1, the pilot flying must react at V1 at the latest. And that also means that the actual decision must be made a fraction of a second earlier. Let's consider now the go and the stop situation of a contaminated runway. I think it's quite obvious that in case of a stop before V1, we have to be able to stop the aircraft within accelerated stop distance available, regardless of conditions. We also know that any contaminant significantly reduces the braking action at the same time increasing the ground distance necessary to reach a certain speed due to impingement drag and displacement drag. To make sure that we can stop the aircraft within ASDA, V1 wet has to be lower than V1 dry to compensate for both increased roll distance to the V1 and impaired braking action in case of stop decision. In case of go, a lower V1 will also have consequences. With an engine failure at the most critical moment, right after V1, we still have to satisfy requirements for takeoff distance. However, this time, the required screen height with V1 wet is only 15 feet within total. So, coming back to the question, the correct answer would be answer number 4. Wet V1 would be a lower value. And this is also a correct answer. That will be it for today. Thank you very much and hopefully see you next time.